All right, today we're looking at roots and zeros. It's going to be a continuation of lesson 5-6. If you can remember, in 5-6 we talked about synthetic substitution and how we can use that to kind of help get our factoring process started. Well, today we're gonna take it a little step further and try to find all roots. If you noticed on that last assignment, most of your answers were nice integer numbers, and they were all real answers. Well, now we're going to get into the possibility that answers aren't always real. They could be real or complex. They could be rational or irrational. All right. So first things first, just a little vocab revisit. Zeros, factors, roots, and our x-intercepts all basically mean the same thing. All right, those numbers all coincide with each other, so we kind of use those interchangeably when we're solving. Okay. I mean, we've already talked about that, so we're gonna move on. We won't spend a ton of time dwelling on it. The fundamental theorem of algebra is kind of a big concept here. All right, going into the day, and we've kind of hinted at it throughout time, but every polynomial with a degree greater than 0 has at least one root in the set of complex numbers. Okay, and then a corollary to this theorem is essentially your degree equals the number of total roots. Okay. So essentially what we're saying is if you have a degree 2 polynomial, quadratic expression, there are two answers, whether they're real or complex. There's two answers. If we have a degree 7 polynomial, there are 7 roots. They can be real or complex. All right. And we've kind of hinted that up to this point. If there's, a degree 5 polynomial, there's up to 5 real roots possible. All right. So we're just going to dive right into things again today. They don't have to be nice numbers. They can be rational, irrational, real, not real. The first few problems here are actually going to be factorable expressions, and I'll show you when or what to do when you can't factor it. Okay. Factoring, again, is probably the easiest thing to do, so I would always check your problem first to see if you can factor. Like on example 1, I see a difference of 2 squares, so I'm going to factor it using that pattern x squared plus 4, x squared minus 4. All right, at this stage, we can factor again because we have another difference of squares right there. So that winds up into x plus 2 and x minus 2. All right. At this stage, our expression is factored completely. Remember, sum of squares, x squared plus 4, we cannot factor because those answers are complex. All right, and then we just need to solve. So we wind up getting an answer of 2. We end up getting an answer of -2. Remember, to solve, we set each factor equal to 0 and solve. Here, we'd subtract 4 and square root, which means the answers here are plus or minus 2i. All right. It says state the number and type of roots. I'll do that in a different color. All right. Our degree is 4, so there's 4 roots. All right. And after looking over our answer, it looks like we have 2 real and 2 complex. All right. Hey, there's a corollary we just talked about earlier on the bottom. No big deal. All right. So again, factoring is a great way to solve. Look for those patterns. In the next case, we have 4 terms, so I might try to group right away. All right. We're looking to solve. Again, the point of factoring is to get it to a point where we have multiple factors we can set equal to 0 and solve. We're going to take out an x squared, which is common. We wind up with a 3x minus 1. Take out a 3, we're left with 3x minus 1. then we can factor again. So 3x squared minus 1, and x squared plus 3. So again, we can solve. If we set this factor equal 0, add 1, divide by 3, we get 1/3 as our answer. This one here, if we subtract 3 and square root, we're going to wind up with plus or minus I root 3. So at this point again, we know our degree is 3, so there's going to be 3 roots. And it looks like we have 2 complex and 1 real. Or you could say 2 imaginary. If you want to say imaginary. Imaginary. Because those have that I component to them. Okay? Keep in mind today as you're going through things, complex answers always come in pairs. So if I tell you 3i is a solution, you know that negative 3i is the solution as well. All right. The corollary on the bottom we addressed earlier. So let's continue on. All right. On some problems today, you're not actually going to have to solve the entire thing. We're going to use what's called Descartes' rule. Descartes, Frenchman. All right. And basically what he discovered is when working with polynomial equations, he was able to determine the number of positive solutions, number of negative solutions, and then from those you could derive the number of imaginary solutions based on the corollary we talked about before. So if we have 2 real solutions, but it's a degree 4 polynomial, that means there has to be 2 imaginary. Okay. And that's what Descartes' rule talks about, okay? And the big thing we need to do is we need to figure out how many sign changes are in P of X, and we need to figure out how many sign changes are in P of negative X, okay? P of X tells us the positive real zeros, all right, the number of sign changes. And then P of negative X tells us the negative real zeros. And then the big thing here is or less than by an even number. And we say even number because remember complex answers always come in pairs. So if there's a complex answer, it always has to be in multiples of 2. Okay. So this looks really confusing right now, and there's a lot of words there. It really isn't that challenging, and I'm actually going to move the definition and kind of explanation out of the way, and we're just going to go through it together. So first things first, you want to take your function as is and determine the number of possible positive real zeros. Okay, and I'm going to do it in blue so you can kind of see. So I want to look at my function and I want to check out the sign changes. So we go from positive to positive, from positive to positive, from positive to negative. So that's going to be 1, from negative to negative, and negative to positive. That's 2 sign changes. Okay. Then what I want to do is I want to do the same thing with f of negative x. All right. So if I think about this, if I take negative x to the 5th, it's going to stay negative. If I take negative x to the 4th, it's going to stay positive. If I take negative x to the 3rd, negative x cubed is negative x cubed. So I wind up with negative x cubed. Negative x squared is a positive x squared. So then this is going to stay as negative 4x to the 4th. The opposite of negative x is positive x, and then we have that plus 9 to finish. All right. So then from here, sorry, to just reiterate what we did, we took negative x and plugged it in to our original function and just evaluated. Okay. So now we want to do the exact same thing we did before. Count the number of sign changes. So we go from negative to positive, so that's 1. Positive to negative, that's 2. Negative to negative. Negative to positive, that's 3. Positive to positive is not a sign change. All right. So before we move on to things, I want to state my degree is 5, and this will help clarify things. Okay. So to kind of reiterate what we did on this problem, we're trying to figure out the number of positive or possible positive real zeros, meaning positive x-intercepts on my graph. I'm also trying to figure out possible negative intercepts on my graph, which are 1, 2, and 3. All right. And once I have those answers, then I could find out the number of possible imaginary zeros of the function. All right. So looking through things, we have positive real possibilities. All right. So if you notice, there's 1, 4, 2. Sorry. Not 1 or 2. Okay. So we count the number of sign changes, and it's always going to be that or less than by an even number. So it's always going to be 2 or 0. We had 2 sign changes, so it's 2 or 0. If I had 4 sign changes, it would be 4, 2, 0. If I had 3 sign changes, it would be 3 or 1. If I had 7 sign changes, it would be 7, 5, 3, or 1. Okay, so you always take the maximum number of sign changes and reduce it by an even number. So 2 or 0. All right. So now we're looking at negative real possibility. This possibility. Sorry, we're running out of space there. So in this case, we had 3 sign changes. So we know we're going to have 3 or 1. All right. And then this is kind of the fun part. Imaginary possibilities. All right. It's kind of like a puzzle. All right. We know the degree of our polynomial is 5. Okay. So let's kind of go through things. If I have 2 positives and 3 negatives, all right, so I have 2 x-intercepts and I have 2 positive x-intercepts, 3 negative x-intercepts. That's already 5 zeros, which means I would have 0 imaginaries, because a degree 5 polynomial can only have 5 zeros. All right. If I have 2 positives and 1 negative, that's a total of 3 real zeros, which would mean I have to have 2 complex, because I need to have a total of 5 roots to this problem. So I had 2 positives, 1 negative, that's 3 real zeros. That means I have 2 complex. Okay. And then we're going to do the same thing with the 0. If I have 0 positives and 3 negatives, that's a total of 3 zeros. So I'm going to need 2 complex to fill that out. Okay. If I have 0 positive and 1 negative, that means I'm going to have 4 imaginary, because I need to have a total of 5 answers to my problem. All right. So again, to kind of walk you through this problem, you want to count the number of sign changes in the original function. You want to plug in negative x, count the number of sign changes in that function. All right. That's going to be the maximum number of positives in the original. When you plug in negative x, that's the maximum number of negative real possibilities. And then you want to piece it together. Okay, keeping in mind the degree of the function on those problems. All right, because you're never going to have more than 5 answers in this case. All right, complex conjugates theorem, we already talked about. It's if you have a complex answer, they always come in pairs. The last thing we're going to look at today is not just finding or classifying zeros, but actually writing functions. All right, so it's a little wordy, but all we really care about are these two. All right. And this is one of the more challenging questions, because we do have that complex answer in A plus BI form. All right. Keep in mind, when you're writing a function, you guys, all right, you know, we have, you know, all of our factors, blah, 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 and any coefficient in the problem. All right. It says, write the function of least degree with integral coefficients, so we can't have fractions in the problem. Okay. And then it says the zeros, which include -1 and 1 plus 2i. Well, if my answer is -1, I know that one of my factors has to be x plus 1. We do the same thing with this answer. So x minus 1 plus 2i. But keep in mind, complex answers always come in pairs, all right? So if I have x minus 1 plus 2i, I need to have x minus 1 minus 2i, okay? Complex answers always come in pairs. Now this looks a little confusing because we want to write our function, but we have I in the problem. Well, how is this going to work out? Well, what you want to do is FOIL these factors. And by FOIL, I mean just distribute everything out. So we wind up with x squared minus x minus 2ix. If I distribute the -1, I'm going to get negative x. I'm going to get a positive 1. And I'm going to get positive 2i. If I distribute 2i, I'm going to get a positive 2ix. I'm going to get a negative 2i. And then I'm going to get a negative 4i squared. All right? And some of you might be like, well, why did he just write it like that? Well, our negative x's go together. 2ix's drop. 2i's drop. Remember, negative 4i squared is going to be positive 4. So then we end up with plus 5. Notice how nicely that worked out when our complex answers come in pairs. When we, put them in factor form and multiply everything out, the i's are going to drop out of the problem, which makes sense. Then the last thing we need to do to figure out the final polynomial is distribute out the x plus 1. So we wind up with x cubed minus 2x squared plus 5x. We have x squared minus 2x plus 5, which means our polynomial function of least degree is x cubed minus x squared plus 3x plus 5. All right? And that's how we do things today, all right? Again, to kind of recap and revamp things, all right? First things first, you always want to try and factor your expressions when solving. Make sure that your number of answers does match the degree of the function. If you have a double root, it counts as 2. So if you had like x plus 2 and x plus 2, you only have to write the 0 once, but just remember in the back of your mind that does count as 2 answers, okay? Secondly, looking at Descartes' rule, we want to count the number of sign changes in the original function, and when we plug in negative x, we can use those answers to determine the possible roots on our graph, and furthermore, we can, the possible imaginary roots. And then the last thing we're going to look at is when given answers, come up with the polynomial function that goes with those. All right, so kind of working backwards as far as things go. Assignments on the bottom. If you have any questions, you are welcome to chime into the live session or ask on the discussion board. Otherwise, I wish you all the best on this. I hope things go well. That's all I got.